Nicola, mi senti? Non mi sente niente.
Okay, just a few steps back. So a beginner type. Here, it is like, I mean, we call it chromatic type for the representation here. Which is like a homomorphism, some kind. And let me just step back at the very beginning of the theory. So basically, what we want to have is like some growth condition. Okay, this is like in Fourier type, Fourier representation here. You have some growth condition on F, and you want to show that this is equivalent to a growth condition at the head. And typically, one of these directions is easy, and the other is less easy. So the easy one is to show that okay, typically that's easy, that's hard. Let's say typically this is deep in some sense, and this is shallow in other sense. At least in some instance. So the basic example, this is before Peregrino, like in Fourier representation or Fourier inversion theorem. If you have a function f on minus 5, 0, 5, C, and if you let Fourier coefficient, I don't know want to have normalization or not here, without normalization, 0 to 5, f, you combine R and D, then we have the function f can be reconstructed in L2 as a sum, and I'm sure there is a coefficient 1 over 2 pi. That's to put it over f n. This is for n integer p to the I and t, and the big is going in this and the integral of f square t is equal to then I guess I want to put some 1 over 2 pi 1 over 2 pi. I'm sure I'm missing some position here. Square. Say this is 1. Okay, if f is 1, then this is 2 pi square, and 2 pi square, that's the one this is 2 pi. Okay, and this is going into the D direction. This is the reconstruction formula here. It's going in this direction because it requires the completeness of the trigonometric system. Which is not trivial. Okay. Okay, so this is going into this direction. A growth condition on F, which is this is finite, implies a growth condition on second. The other direction, so this is called the spectral analysis of F, and the spectral synthesis, it is if I have a sequence AN in L2, and I make up the function F from AN in I and D, then the L2 norm of this function then and this function converges in equal L2. This is the spectral synthesis. And it does not require completeness, it requires just orthogonality of these objects here, which is trivial. Okay, and then Nichols. Okay, so this is like a Fourier inversion theorem, which is the deeper side. And Nichols showed already a holomorphic version of that, in which we had, okay, say, I get the sequence for the holomorphic version. That it is I get the sequence n, but this time I want n positive, and to this sequence I associate n of z sum of n such n. And it's easy to see that this series converges from not z as a 1 if if I have this growth condition here, it's easy to see that this series converges, and that okay, and this is the end. Okay, now we don't look. Okay, this function here is defined inside, not here a priori. It is defined inside the unit, and so we want to reconstruct to have a norm which depends on the value of inside, and this is later we consider the integral between 0 and 2 pi of f r e to the I t mod square P over 2pi, and we take this premium, which is same as the limit for r than 1. So we consider the function on a smaller list, and this is equal to some. Well, and that's the easy part. The easy part, which means that is the simplest part. Because the proof of this just requires the orthogonality of this. And the hard part, so to speak, is the other one.
Sorry, cannot see the last line of the Blackboard.
Oh.
Okay.
Okay. And the analysis part. Better analysis part, which is deeper, says that if f is a normal function and this premium for r equals 1, that thing of f t finally then f will be written for the n is equal to the limit from 1 integer t also. Okay. And this is bigger because it requires the completeness of the. Okay. So in this Bailey-Wiener kind of version of Fourier inversion, the defect is that we only rely on the values of the function f, where f is the format. So this long introduction to say, okay, by the way, we have not mentioned them anyway. Okay, here we're talking the Bailey version, Bailey-Wiener, which is the hard space of unities. Okay, then you can wonder in which sense you have found the values for f, and this opens very interesting area which I'm not sure to talk about today. So now recall. Okay, recall what is. A with a positive is given by the functions f. So these are a priori, to start with, these are functions f defined on the real line. F equal to 2, so that the support of f they minus 3 over 3. And now and because that we have the reducing kernel for these functions here, the f of x is that the inner product over A and Y is equal, if you remember what that, time phi A minus Y over phi. So the first thing is showing that X extends to a holomorphic function, entire function, to a function X, it is holomorphic to Julia. We just keep it on the user introduction. Okay. Defined as the integral between minus a over 2 and a over 2 over omega e to d. Now let me see if I want to have yet. 2 pi omega. Okay, where f hat is the transform of this real functions on R, and we extend it from Z real to Z meaning of this. Okay, so basically, so this is the shadow part. Is that the part? Because basically the idea of the proof it is that the function into the 2 pi omega z is a holomorphic. So this is like a linear combination of holomorphic functions. So it is a holomorphic. Of course, you have to prove convergence in some kind. So basically, any operator related to homomorphicity applied to N, you take it inside the integral, but this one, you could do it with the bar operator, or do it with a Cauchy integral, or you could do it in. So we do it with a Cauchy integral. By the way, I forgot. An estimate. Moreover, we have time. Let me put here another piece of the thesis. Moreover, we have the estimated modulus 10%, that's equal then square root of 8 times the modulus F times 12 times e to the power and here I put modulus that, but actually modulus that. So how do we prove that it is homomorphic? We pick just the curve gamma in the complex plane, and we verify that we can take the integral inside. So suppose gamma is close. And then we have the okay, we want to get the integral of on gamma of z is equal to the integral of minus a over 2 omega minus I omega z is equal to the integral of so we take switch order integration, so we get that and integral over gamma of I omega z. I guess the omega, and that's here for gamma, and then by Morello's theorem, that implies that the homomorphism. So the complete order of integration. So we get the switch order of integration in some kind of Fibini theorem. So this double integral over here, really, it is so let's go this I. So really I is the integral between A and B. Oops. Maybe A is not against alpha and beta. Between alpha beta of the integral with respect to the variable t of gamma dot t of omega I omega gamma t omega, and if you consider, so we take the integral over this rectangle, you set to these variables of the function h of omega, which is gamma dot by I omega gamma of t, and if you consider the modulus of this, okay, this is bounded by a constant. Omega times, but this is with omega 2, and then this is like e to the 5 a over 2 times constant. And that's okay. This is the L2 of minus a over 2, so it is in L1 of this by which is short quality. So this is a function which is positive and is in L1 of data. So you can use convenience. Right. constant, everything. And I have here. So switching integrals to justify them, so I have zero. What about the estimate for that? But that's the way the model inside goes that. Let's read and here we get we have the explanation, so we get the real part of e to the 2 by I omega z. No, the modulus. No. Okay, but the sheet part that's lesser equal than the normal left. Where it's a square normal left square, what that has is square, take the integral between minus a over 2, and this is into the real part of that, which is e to the minus. I have to take a square for pi omega, and here I get imaginary part of z 1. The omega and the okay, I could write this like a hyperbolic sign, but really the biggest possible value is for length of the interval, and the biggest possible value is easily by and also e to the 2 pi a, which is positive, y, which is right. Okay, so that's the easy part. And the theorem of David-Wiener, so we showed so let me, so the proposition said that if f then f of z let what you said f omega by omega z. Omega defines the function f, which is the homomorphism, and it is of exponential type. It is f of z, that's very equal to a constant times e to the pi I modulus of the imaginary part of z, which is pi a modulus z. So it means that it has order, at least at most one, okay, so the order of f is at most one, which is the power here, and we have more precise information. We also know the constant to put on top of that. So it is of exponential type. So Peltier here, it is the other way around. Okay, so here we have okay. So in this case, we did this synthesis part. We started with something in L2 and constructed a Hormone function and showed that the function has some growth. Okay, we start with f hat, I mean some growth, and the function we construct has some growth. Pellinger theorem goes the other way around, and there is this much. So here is Pellinger. Says that if the hormone in the genetic function and X satisfies that condition over there is a constant and that and when I consider F restricted to the real line, this is in L2. Okay. So we have a complex plane of real line. F restricted to that is in L2, then F hat, which is the transform of this thing, is supported of F hat. Rise over 2. Well, and this hat by the proposition allows one to reconstruct the function f. Okay, for the proofs, I looked at two proofs. One is on state monograph on sampling separation, which is very short because there are no details and it makes it easier for finding either of here. And the idea is the proof which does not legal principles, which I got from remember from some letter from a guy analytic number theory. And I think the reference. Okay, so so what is the idea? So the idea for the proof the idea is that I want to write okay, f hat of let me say okay, f hat although that means. Well, we don't know. Okay. So as a head of omega, is the integral when infinity at rest each by omega x I write it as the integral here omega x minus the integral between 0 to infinity, and then on the negative axis I put f minus x and by I times 2 pi omega x dx, and I look at these two integrals as okay, this integral I look at it as an integral here, and the integral like this, an integral here. So why not look at all the integrals that? And to show that all of these integrals are the same, and so they cancel out, provided some factors. So the idea is to extend. So we define for W in okay, maybe I should draw a picture. Okay, this is the complex plane, this is the positive real axis. Now, if I have an angle alpha, which may be positive or negative, I call these lines what do you call it? Gamma alpha, which is like x by alpha. Here, this line. And then opposite to that, at a distance a over 2. So going negative alpha, at distance a over 2, I consider half plane, and this half plane I call it pi alpha. Why do I need this? So that's the definition. For alpha, let's call it 5 and then there is W on this number, 5 alpha W, and the integral okay, on the line gamma alpha over f on e to the how to put it here. Minus 2 by W that and maybe here 6. Yes. I'm sorry, F. This here. Here I didn't put an I. I didn't put an I, it means that these two half lines will be turn 90 degrees. Okay, and so let's try alpha, function which is homomorphic in phi alpha. In phi alpha. Phi alpha is this one, which is the statement of order, how we call them, W's. So these are the W's that rotated back in the carton of E minus I alpha carton A over 2, which is rotated back, they are distance A over 2 on that. And observe that we have two spatial cases, which is when we have pi which is pi 0 and pi pi. Okay, pi 0 and pi pi, they are more okay. Pi 0 is defined as a bigger thing, which is the set of W, so that the real part of W bigger than 0, and pi little pi is W's. So when alpha is equal to 0, alpha is equal to pi, it's planes of these. Okay, so let's show that these things are defined. I just think
I didn't understand that.
the last thing. The last thing is that
No, why pi 0 is that? Why is pi 0 is that?
because in pi 0 we can use because in pi 0 we can use the fact that the function is in L2.
No, so you defined pi alpha that way.
Yeah.
But when I put alpha equals to 0, I don't get what you write.
Yeah, those are exceptional.
Yeah.
So this is pi alpha is the homomorphic here for alpha bigger than 0 pi, and these two things. So these are bigger.
Sorry, I still cannot see the last line.
Sorry. Can you see?
Yeah.
Yeah. Because the idea is that when alpha is equal to 0 or pi, you are on the real line, and on the real line you have not just the growth of f, but you also have the fact that f belongs to L2. So you can use. Right. Let's check it. When we have phi alpha w, which is this one, phi alpha w. So consider just in generic case, phi alpha w, that's equal to the integral between 0 and infinity, because here we are on this line of x e to the I alpha times E minus pi omega and e to the I alpha D delta, which is like I maybe something very interesting x and we take side we take the modulus inside and here we get okay, for this we have constant times e to the modulus of that, which is to the 5 alpha x. That's why the growth condition.
A, no.
A. A. And then here we get the real part of that, which is e to the pi extra real part of W is the alpha, I alpha. There it is. Extra. And the real part of that, which was bigger than A over 2, right? So after this constant, that to be pi A pi S pi S 2 pi S, say, of A over 2 minus that. Okay. So for W fixed, this number is less than 0. And so this converges, and if this converges.
There is a small thing with the signs, because here you wrote e to the minus I WB.
You're right.
Do you have that bar maybe in the numbers?
Because maybe I have that part. Yeah, I should have that bar. No, I don't want to have that bar. Because it has to define a homomorphic function.
No, but you are.
Sorry, the last part of the integral is real part of what? Omega?
Real part of W into the I alpha, and maybe I don't do this.
No, the W will be polymorphic. That you can put the bar in the Z.
No, it is when I place because it has to be polymorphic with respect to this value. F. Oh no, you're right. No, but that's the definition.
I mean, a bar in the.
Yeah, you're right. Because if I put the bar here. Then I then minus here. Then minus here. Yes. Yes. Yeah. Yeah. Okay. Which converges and okay, if alpha is equal to 0, if alpha is equal to 0, then we have a bigger because so if it converges, then I can use Frobenius theorem, Morera's theorem for define that for one function. And for plus Morera. One. Where it is defined. And okay, when alpha is equal to 0, we have some extra information because we have integral of 0 infinity and e to the minus I alpha is equal to 0, so that's 1. So that's W. W U plus IV, say, and that's
Sorry, I cannot read the exponent.
You cannot read it?
No, it's really the video is not quality, so I cannot see the exponent. What is?
W is equal to U plus
No, the exponential. I mean, what is the
it's e to the minus
I
2 pi. There is no I. W
okay?
S. S, which is e to the minus 2 pi U S times e to the whatever something other I B S. S. Okay, and when I take this absolute value inside, that disappears. This is integrable if U is bigger than 0. If U is bigger than 0 with S between 0 and infinity, that's integrable, and so basically that's so equal than that times the L2 norm of the function associated to f possibly yes to f into the minus 2. So we can play the same whatever. Okay, so so let me say. Okay, in also it was
So the last term is the function that maps S to
e to the minus 2 pi US. This one.
okay.
This one. Because I take the modulus inside. And then I use Morera. After I have the integral convergence, I use Morera. I guess it was more precise than here. Okay. And now, before the well-researched break, I just draw a picture, and the picture is like this one. Draw picture this, which is the next picture from the next lemma. The next lemma says that for alpha, for beta, it's alpha between 0 and 5, we have that phi alpha is equal to phi beta on the intersection of the which is the so we're going to verify that so here we have alpha and here is beta. So that beta, that's alpha, and then we turn things around. And a distance A over 2, we consider pi beta, which is this one. And here we have pi alpha. So in this intersection, so in this angle here, we have the function is the same. And this allows us to move things to the end. Okay. Okay, let's have a minute, sorry.
With this definition, this is different from definition that you wrote before for pi alpha. With this definition, you don't need the bar in the.
Yeah, for the 0 we don't need.
No, it's a matter of reflection that you wrote, as you wrote pi alpha, it's just perpendicular to gamma alpha. If you don't put the minus on the exponential, is this one that we draw now?
Okay, gamma alpha is here.
So I don't know what was the definition you wrote for pi alpha before. It was the real part of e to the minus alpha I.
I thought it was e to the plus. No.
No, the black one you wrote with the minus. That's why I.
Oh. I was wrong.
It's a matter of.
I mean, okay, it's a matter. I mean, pi alpha, which is the one in the picture,
Okay, is with the plus.
it is with the plus. So if I'm sure I wrote the wrong sign. Bigger than 0.
Yes. And then you
Which is RBWs that rotated back have the real part bigger than rotated back, the real part bigger than. Yeah, there is plus here.
So you don't need the bar in the, there is no problem with the bar before.
Oh,
If you, it depends.
Okay.
If you define pi alpha like this, you don't have to, you don't put the value in the definition of pi alpha. Because there you get the minus,
You're right.
but it's the same.
Okay, there are signs are screwed up a little bit. Thank you. I hope on the office better, correct?